Hi, everyone. I'm Chris Humans. I'm a faculty member at Caltech, and I, among other things, I teach the Intro to Theory course, which this lecture is part of. And I've done that every year for many, many years since I've been here. And I really enjoy the material. It's actually this lecture, which is about NP completeness of 3-SAT, is one of those things that sort of got me hooked on theoretical computer science in the first place many years ago. So it's really fun to be able to give this lecture. My research is in complexity theory, having to do with the study of randomness in computation, which is sort of a related question to the P versus NP question, or analogous to that. I also work on algebraic algorithms and algebraic complexity. All right, so let me share. So I'm going to do this with slides. Share now. Okay. Okay. So NP completeness, the Koch-Levin theorem. So let me start. Let me start by actually being able to advance the slides. There we go. All right. So let me start with a puzzle, just to sort of introduce 3-SAT. And actually, this is a really good way to think about 3-SAT when you're doing reductions from 3-SAT, which is part of what you'll probably have to do with this material later on in the course. So this is a little bit of a contrived puzzle, so just bear with me for a minute to while I describe it. So the challenge is the following. So it's a question about whether you can find an efficient algorithm to solve a problem, whether you can find a polynomial time algorithm to solve a problem. And the problem is as follows. You get a bunch of triples of symbols, which in the slides I've just indicated using characters. The symbols are alphabet characters. They're either uppercase or lowercase letters. There's 2 kinds of each type of symbol. So you get a bunch of triples of these, a long list, probably longer than these 4 that are indicated here. And the challenge for your algorithm is to look at such a list as its input and to determine if it's possible to select at least one symbol from each triple without selecting an upper and lower case of the same symbol. So the red characters on the slide is an example of a way that this sequence of triples is we would say a positive instance. There is a way to select one character from each triples, which is indicated in the red here. But there could also be sequences of triples where it's not possible. For example, the pair of triples, which is, all, the first one is 3 capital A's, the second one is 3 lowercase a's. There's no way to do this, right? Because you're forced to choose both an uppercase and a lowercase a. Okay, so the challenge is, given a sequence of triples like that, find an algorithm to identify which type this is. Either it's possible to circle one symbol in each triple without uppercase and lowercase, or it's not. And that's a sort of a combinatorial type puzzle, and it's one that you could imagine kind of trying to devise an algorithm for. I mean, many of you might start to think about something where you kind of do a branch and bound, where you maybe choose one thing in the first triple, and then you go down the line and keep choosing the first one that's available to you until you see that one's not available, and so you have to backtrack and try something different. And if you play around with this a little bit, you'll find that there's lots of different approaches you can imagine that all seem to take exponential time. So the challenge is, can you find something that takes polynomial time for this? But anyway, that's a problem that is good to keep in mind, a puzzle that's good to keep in mind. And the reason that it's relevant for this lecture is that it's a disguised version of the language 3-SAT, which is the problem that we're going to show as NP-complete. So 3-SAT is the language consisting of those Boolean formulas that are in conjunctive normal form with 3 literals per clause for which there exists a satisfying truth assignment. And just to unpack some of that, conjunctive normal form just means that the formula, which an example of which is written down here, is the and of ors. Okay, so these are ands that connect things, and then there are ors inside each of the parenthesized expressions. And each of those parenthesized expressions is called a clause, and each of the variables where its negation is called a literal, and there are 3 of them in each clause. Okay, so and given such a formula, the three-set language consists of those formulas for which there is a truth assignment to the variables that causes this whole expression to evaluate to true, satisfying truth assignment. Okay, now that I'm claiming that that is the same thing as the sort of puzzle problem that we identified on the previous slide. That is to say, if you have an instance of the puzzle problem, which is the sequence of triples like we were looking at before, then you can translate that into this three-set form by taking like the, the letter A becomes the variable x1, uppercase occurrences appear positively, and a lowercase occurrence occurs as a negation of x1. And then B gets translated to x2, and since there's a lowercase b, it becomes negated x2, and so on. And I think that you can see that if there was a way to choose one symbol from each triple among this sequence of triples, well, if you make those corresponding literals in the clauses true, and then set anything else that's not set any way that you like, what you'll end up with is a legitimate, satisfying truth assignment, because you'll have one true, at least one true in each clause, which is enough to make this whole expression true because they're connected by ands. And because you never circled an uppercase and a lowercase, or never selected an uppercase and a lowercase of the same variable, it's a legitimate truth assignment. You're never going to try to set x1 to be true and not x1 to be true at the same time. Okay, and it works both ways. If you have a truth assignment to these, oops, to do that. If you have a truth assignment to these, to this 3CNF formula, then you can just select, you know that if it's a satisfying truth assignment, it has to have at least one true in each clause. You just pick one of those true literals and select that for your selection among the triples, and you will never choose both an uppercase and a lowercase of the same character because it's a legitimate Boolean truth assignment, because it's a satisfying assignment, there'll be at least one to choose from every triple. Okay, so there's a correspondence between these two. And I mention this just because having both of those interpretations in your mind is sometimes useful when you're doing reductions from 3-set. And also because it sort of explains why it plays such an important role in the theory of NP completeness, which is what I want to say next. Let's see here. So the Cook-Levin theorem, the topic of today's lecture, is the theorem that states that 3-set is NP complete. And I wrote that that's the gateway to proving lots of natural important problems are NP complete. And that's because 3-set has this sort of puzzle flavor to it, which I tried to bring out, combinatorial puzzle feeling to it, or at least combinatorial feeling to it, that doesn't make explicit reference to computation in any way. But because it has this sort of combinatorial puzzle feel to it, it can be easily reduced to lots of other problems that have to do with combinatorial type puzzles, like other problems that you might have seen or will see, depending on how the course is organized, like vertex cover, Hamilton path, clique, other graph problems, and thousands of other problems. But they all tend to have this sort of combinatorial feel to it. And because 3-set is NP complete, that gives a starting point for lots of reductions. Okay, so that's the theorem we're going to try to prove today, or in this lecture, I should say. And I need to just remind you of a couple things which are probably have already been covered, but just so NP is the set of languages that are decided by polynomial time non-deterministic Turing machines. You know that. An alternate definition of NP, which you probably have also seen, which is important for this reduction, is this theorem that a language is an NP if and only if it's expressible in the following form. So the language is expressible as those strings X, for which there exists a Y, another string, whose length is at most polynomial in the length of X, such that the pair XY is in a language R, where R is something you could decide in polynomial time. Okay, so the language can be a language that's in NP is expressible as those strings X, for which there exists a Y, such that XY is in R, where that's something you can decide in polynomial time. And that's a nice thing because it doesn't make reference to non-determinism. It just talks about polynomial time computation, which is easier to think about. Okay, and then if you actually wrote down a Turing machine that decided that language R, you might call it M sub R, That's sometimes referred to as a verifier because it does this checking to see if XY is a member of R. And there's a couple of other bits of terminology that are associated with this. The string Y we sometimes call a witness or certificate because the existence of such a Y is a way of proving to yourself that X is a member of the language. If you have such a Y such that XY is in R, then you know that X is in the language. And if not, X is not in the language. And this feature that you can determine whether X is in the language or not by the existence of a witness that can be checked efficiently is sometimes called the property of being efficiently verifiable. Okay, and so this is just another, this the theorem we're not proving now, but it's another definition, if you will, of NP. It's equivalent to the standard definition in terms of non-deterministic Turing machines, or you might have seen this one first. That's going to play a key role in the reduction. Okay, so the reduction is going to come in two parts. So first we're going to show that a related problem called circuit sat is NP complete. And circuit sat is just the same kind of thing as 3-sat. It's just that the instance is no longer a 3CNF formula. It's not something in that special form. It's just a arbitrary Boolean circuit. And I'll remind you what that is in just a minute. And the question is whether that, so the language consists of those Boolean circuits for which there exists a satisfying truth assignment. A Boolean truth assignment to the variables that makes the circuit output 1 or true. So that's the first part of the reduction. And then the second part is we're going to show the 3-sat is NP complete and we'll reduce from circuit sat. Okay, so let's start with the first half. We're going to show that circuit sat is NP complete. I promised you I would remind you or tell you what a circuit is just so that we know what we're working with. So a Boolean circuit, C officially is it's a directed acyclic graph. In the picture I've indicated the nodes. Each node is labeled with an and, an or not, or with one of the variables. Okay, and or not, or one of the variables. And here's a little picture of one over here. I guess the important thing to notice is that the fan out can be more than one. So like, for example, this AND gate here, maybe I should have drawn a circle around it as the node, has its output going out to two different places. And in general, that may be true for any of the nodes of this circuit. So for example, the variable x2 may have its output going off to different places in the circuit, not pictured here, but that's possible. Okay, and I think you can probably see that if you choose a truth assignment, whoops, I don't want to do that, sorry. If you choose a truth assignment to each of these variables x1 through xn, then there's a natural way that that truth assignment propagates up through the circuit. So x1 and x2 combine with an and to put whatever truth assignment belongs at that node there, and the other truth assignments propagate up, and then some truth value, true or false, pops out the top of the circuit. So in this way, a circuit C naturally computes a function from n bits to 1 bit in the way that we just described. And when we talk about the circuit, we're often going to sort of deliberately confuse the circuit, which is the graph with the labels on the nodes and so on, with the function that it computes. So we'll identify those two things. And the size of the circuit is just the number of nodes. Okay, so that's Boolean circuits. And then the one fact that we need about Boolean circuits, just to observe, is that any function that you can think of from n bits to 1 bit can be computed by a circuit of a certain size. The size is not so important for this argument, but in fact the size can be, let's say, n times 2 to the n for an n-bit function. I'll try to convince you of that here, and then that's just going to be needed at one later point in the proof. So one way to do it, there's many ways to do that, would be to say that you identify each of the x's, like, so this is a, x is now a vector of n variables. So each of the n-bit strings for which the function evaluates to 1, and you can construct an and of n literals associated with that x that evaluates to 1 on exactly that point and 0 everywhere else. Okay, so like if the x that you were thinking of was 1 0 1 1 1 1 1, then that and would be the and of x1, not x2, x3, x4, x5, etc., and so on. Okay, so you can construct an and of n literals for each x that evaluates to 1 on exactly that point and no others. And then you can just take the big OR of as many of those as you need to take care of all of the points at which the function evaluates to 1. Okay, and if you put that all together, the circuit you end up with has size at most n to the times 2 to the n. In fact, you can do better than that. You can do 2 to the n over n, something like that, but that's not important for this lecture or even this course, probably. Okay, so that's Boolean circuits. Okay, so now we're at the point where we can actually try to show the first part, which is that circuit set is NP complete. And there's theorem. Okay, so we're going to try to show that circuit set is NP complete. I rewrote in blue here, I guess, what the definition of circuit set is, just to remind you. To show that something's NP complete, as you know, we need to do two things. We need to show that it's in NP and then give reduction from every language in NP to that circuit, to that language, I should say. And so our first part, we need to show that, in the first part, we need to show that circuit set is in NP. And this is not too hard. In fact, we can use that alternate definition of NP that we discussed. We can express circuit set as this, which is this language, in the following way. We can express it as those circuits C, where C is a Boolean circuit, for which there exists an X such that the pair CX is in R, where R is the language which takes a pair, which is a circuit and a string, and just accepts if that circuit on that, I don't know why that keeps happening, that circuit on that string evaluates to 1. Okay, and I think you can see that that is another way of just stating the language circuit set, and it fits the format that we said was an alternate way of defining NP. There's the witness. The witness is the string X or the assignment, and it can be checked in polynomial time because you can check, given a circuit and an assignment, whether that circuit on that assignment evaluates 1. Okay, so it's in NP, and let's now proceed with the reduction. So again, there's the definition of the problem, the language. And now we need to do this reduction. So for each language in NP, we need to give a polynomial time reduction from that language to circuit set. So, you know, this is a generic reduction in the sense that we're taking an arbitrary language in NP and carrying out this reduction. And, you know, one of the things that kind of guides you when you have a generic reduction like that is that you don't really know much of anything. So what do we know about A? Not much, except that it is a language in NP. So it means that it can be expressed in the following form. It can be expressed as the set of X, such that there exists a Y, such that XY is in R, where R is some polynomial time language, meaning that there is a Turing machine M sub R that decides this language R in some polynomial time bound, and let's give it a name, n to the C, and we'll call it G of n, n to the C for some constant C. Okay, so that's our generic NP language, and we're now going to try to reduce that to circuit set. And to do that, we're going to use something called the Turing machine Tableau. Now, I'm not sure if in an earlier lecture you would have covered this, so I'll just tell you what it is here. I hope that you do know, however, what a configuration of a Turing machine is. So configuration is sort of instantaneous description of the Turing machine. It has the contents of the tape and the position of the head and the state. And if you organize those configurations of a Turing machine M sub R on a given input as it runs, you organize those configurations one after the other, one on top of the other. That's called a tableau, and then you kind of pad them out so you make a nice array. So in this example, where the input, where the machine that we're thinking about is M sub R, that's the verifier for the NP language A that we're talking about. So that's our polynomial time Turing machine. It has its input W, which in fact comes in two parts. It's the X and the Y. Just go back. Maybe just go back to remind you that there's the two parts of the input, which are the X, which is the instance of A, and then Y, which is the purported witness. So that is the input, and you know, in the Tableau, we start out with the contents of the tape being the input, W1 through Wn, if it has n characters, and we're in the start state of the Turing machine, which is what this Q sub S means. Oh gosh, why does that keep happening? In the start state of the Turing machine, and that's the entire contents of the tape, and we just pad it out with blanks as far as we need. And then maybe in the next step of the Turing machine, maybe it you know, moves to state Q1 and moves its head over here. So this is the way I'm indicating the position of the head. I'm putting a slash and then the state, and so you can see, you can kind of follow where the head moves and what the state is as it processes things. And maybe in the next step of the Turing machine, you know, you move the head back to the first square, you stay in state Q1, and you write over the symbol here with an A, and so on, and you just keep moving along like that. Okay, so it's just a sequence of configurations of the Turing machine, one after the other, on top of each other. When you think of it, then the height of this tableau, meaning the number of rows in it, is just the number of steps that it takes before this Turing machine finishes, right? So it's the time, the running time of this Turing machine, which is in this case, the length of the input, the length of W raised to the C, which was that constant. And the width is, well, no larger than the amount of time. It's the space usage. It's the number of squares that you end up touching as you execute the Turing machine. And of course, in time W to the C, you can touch no more than W to the C cells. Okay, and then there's one tiny little detail that will be important for our proof, which is that we can always standardize our Turing machine so that it moves its head to its leftmost square before accepting, so that if the Turing machine were to accept, we would see in this leftmost square the state Q sub A, which is maybe the accepting state of the Turing machine. Okay, so the important observation, like the key observation for this proof, and actually just a very important observation about the functions of Turing machines, is that the computation is local. In the context of a Tableau, it means that the contents of a cell in the Tableau is determined by the 3 cells above it in the Tableau and no others. So you only need to look at the contents of the 3 cells above a given square in the Tableau to determine its contents. And I drew some examples here just to sort of illustrate things. So for example, here's the cell we're interested in. And if in this time step, it has, maybe it has state, the head moves into this position, perhaps. Well, we know that from looking at the 3 squares above. We can see that the head, if it was going to move into this cell, it had to be either at most 1 to the left or 1 to the right. So we would see it among these top 3, these cells 3 above, the 3 cells above it. And we would see that the head is in this cell, and that's the contents of the cell, and the state is such and such, Q1 in this case, and therefore we know what the Turing machine will do in the next step. And so maybe we know that it moves its head here. If the cell in question has no head in it, then we would observe that from having seen, for example, that the cell above it has is in a certain state, reading a certain symbol, and so we know what happens. And in this case, the head moves off of that middle cell, and therefore, and we write over that cell with an A. Those are all things you can determine from looking at the contents of this cell in the Tableau, right? And if the head is nowhere to be seen among the 3 cells above the cell in question, well, then that cell has to just stay the same. There's not a head that can move onto it. There's not a head in sight that can cause it to change or be overridden. Okay, so I hope that makes sense. If you look at the 3 cells above yourself in the Tableau, you can determine what the contents of the contents of this cell. Very important. Okay, so now using that idea, we can do the following thing. We can build a Boolean circuit, which I'll call step, which takes the contents of 3 cells in the Tableau and produces the content of the cell in that middle position in the next row. Okay, so it takes, and when I say it takes this is a Boolean circuit, so it takes bits and it outputs bits. So what I really mean is that you've decided upon a way of encoding in binary the contents of a cell in the Tableau. It just has to have a character of the alphabet and possibly adjoined to it, concatenated with it, a character, a symbol which represents the state of the machine if the head is there. So it takes a few bits to describe that, and then it'll take a few bits to describe the cell here. So that's what the step function does. It takes those 3 cells and produces the cell below it. Okay, and again, what I should be careful to say, because we sort of defined a Boolean circuit, and we said, well, that there was a single output bit. So what I mean by this picture and by this assertion is that each output bit in this that's pictured here is some function of the input bits. And you just build a circuit, one for each of them, and put them side by side, and that's the step function that I'm describing. And the key thing is that because this step function looks at only 3 cells, and the contents of each cell is just a symbol from a finite size alphabet, the alphabet of the Turing machine, together with one of the states, and there's a finite number of states. The size of this step function, the size of the step circuit, is independent of the size of the tableau. The tableau may be enormous. The step circuit has a fixed size that depends only on the Turing machine. Okay. So now that we have a little circuit that produces the element of the square of the tableau in the next row, we can just put them side by side to compute an entire next row of the tableau from the row previous. So if we just put, if you remember that the tableau we're thinking about, which is the machine M sub r on input W, it had width at most the size of W to the C. So if we put a whole bunch of copies of the step function next to each other, then we can compute the entirety of a row of the tableau from the previous row. And in the interest of making the picture a little bit cleaner, I didn't draw all the connections here, but I think you can probably see this step function here has inputs which come from this cell, and this cell. This step function has inputs that come from this cell, this cell, this cell, and so on. And you have to do a little extra work to just do something at the end of the line here, because this depends only on the two above it. Okay, so now you've got a way of producing a Boolean circuit that computes one row of the tableau from the next one, the next row of the tableau from the previous one, I should say. And now if you put together those, if you wire together a bunch of those rows of step functions, you can get a big Boolean circuit that computes from the first row of the tableau, the final row of the tableau, right? You just apply these Boolean circuits again and again and again. And then you can do a little bit of work at the beginning and the end to make something useful out of this. You can take some inputs which represent the symbols W1 through Wn, which is the input to this Turing machine. And again, they have to be encoded in binary to make them into a Boolean function. And you can just, there's a little extra wiring that you have to do here to insert this start state of the Turing machine and the head being on the leftmost square. Otherwise, just copy these things down. So that's a little pre-processing you do with a little bit of extra circuit nodes. And then at the end here, you can build a little circuit that just checks whether the contents of this leftmost cell at the very end of the computation contains the state QAccept, meaning that the machine would have accepted that input. Okay, and so that's another little tiny circuit that you add on. So with that little pre-processing and post-processing, you've ended up with a big Boolean circuit which outputs 1 if and only if that machine on that input would have accepted its input. Okay, and then so this circuit, sort of awkwardly on the slide, is called C sub M sub r comma W, because it's the circuit associated with that Turing machine, M sub r, on the input W. It has inputs W1 through Wn, and it has the feature that that circuit on input on the string W outputs 1 if and only if M sub r accepts its input, accepts the input W. And its size, I put in red here, is, well, polynomial in the length of W. And why is that? Because I think you remember we talked about the tableau having size width W to the C and height W to the C for that Turing machine, which runs in time W to the C. And the circuit that we built is just, it has like a little finite size component for each cell in this tableau. So its size is order the size of the tableau. Okay, and actually, I mean, so this is useful for this reduction, but it's also an important statement, which is that we've proved that a Turing machine, the functioning of a Turing machine can be replicated by a circuit, a Boolean circuit, whose size is only the square of the size of the square of the running time of that Turing machine. Okay, which is another important statement, but for our purposes, we're going to use it in just a minute to finish this reduction that circuit set is NP complete. Okay, so let's remember that we're reducing what we're trying to do with all this. We were reducing from a generic NP language, which had the following form, to circuit set. And the reduction, which I'm calling F, which receives an instance of A, a string X, is supposed to produce the following circuit. it is that circuit in blue here, which we've been talking about. It's the circuit C sub M sub R. It's the circuit which simulates the functioning of the Turing machine, which decides R, on input W, which you may remember has two parts, X and Y, and I've written them out here, X1 through Xn, Y1 through Ym. And this circuit outputs 1 if and only if XY is in R. And our reduction does the following little trick with this circuit. It hardwires the input X to be that X that we're reducing from, and it leaves the Y's as variables that are free. So it hardwires the X and leaves the Y's free. And if you think about it, that does what we want, because now you have a circuit where it's got a bunch of variables, they're just the Y variables, and there exists a setting to the Y variables that causes that circuit to output 1. If and only if, well, there exists a Y such that XY is a member of R, meaning, which is equivalent to X being in the language A. So this circuit, once we've hardwired X, has a satisfying truth assignment if and only if X was in the language A, which is exactly what a reduction is supposed to do. So I think, so that's maybe the picture to look at, and then we just sort of say it in words on the next slide. We have to check, at least the way I like to talk about doing reductions, kind of go through this 3 questions. Is the reduction polynomial time computable? Does yes map to yes, and does no map to no? So I'll sort of talk through those, but we sort of saw it on the previous slide. So is the reduction that we've described polynomial time computable? And I claim yes. You have to hard code the description of the Turing machine M sub R, defining a description. The K, which is the length of the witness Y as a function of the length of X. The Y is of the size of X to the K. And C, which is another number which describes the running time of the Turing machine, so some constant. And then the circuit, as you remember, if you remember, has the size of W to the 2C at most. And W has length, which is the length of X and Y together. X has length N, Y has length N to the K. And we need to really argue that you can write down this circuit and compute it, what you're supposed to write down as from the string X in polynomial time. And you can do that because the circuit has polynomial size, and I think you can sort of see from our description of it, it's just you stamp out the same fixed little step circuit just basically in a big grid and hook it up in a predictable way, except for that little bit at the very end in the beginning. So without going into too much gory detail, you can produce that circuit in time polynomial in the length of X. So it's polynomial time reduction. Okay, and then does yes map to yes? So that means, so if we have a string which is in the language A, well, then we know that there does exist a Y by the characterization that such that M sub R accepts XY. And well, that means that the reduction that we produce, that circuit that we produce, is a member of circuit set, because that means there exists a setting to the variables of the circuit, Y, that cause it to output 1. Does no map to no? Well, if X is not a member of A, then for all Y, M sub R rejects, which means that there is no satisfying assignment to the circuit that we've produced. There's no way to set the variables that correspond to Y in such a way that the circuit will output 1. So that's a reduction. Okay, so that's the first part. So that was a reduction that showed that circuit set is NP complete. Now for the second part, we're now going to just proceed to show that 3-set is NP-complete, and we'll do it by reducing from circuit set. Okay, so this was the two-part proof outline that I mentioned before. We finished showing that circuit set is NP-complete. We're now trying to show that 3-set is NP-complete, and we'll reduce from circuit set. Okay, so 3-set is NP-complete. There's the theorem. This is the Koch-Levin theorem officially. I reminded you what the definition of 3-set is. It is those formulas that are in 3CNF, that means and of ors formula, which there exists a satisfying truth assignment. And we talked about a little bit the connection with this, between this sort of Boolean logic kind of question and something that seems a little bit more like a combinatorial puzzle, which helps explain why it's important. All right, so we're going to show that it's NP-complete. We got to do two things. We have to show that this language is in NP, and then carry out the reduction. And a claim that we already essentially showed that it's in NP, right? We said that this, when we talked about circuit set, right? If this, we can express this language as those formulas phi, such that there exists an assignment where that assignment, where you can check given phi and the assignment whether that's a satisfying truth assignment in polynomial time. Okay, so same argument as we had for circuit set. All right, and then for the interesting part, we need to show that 3-set is NP hard, and we're going to give a reduction from circuit set to 3-set. Now, let's pause for a moment before we actually start to do this and think about what does this mean. So we have a circuit, a Boolean circuit. That's our instance of circuit set. And it's either satisfiable or it's not satisfiable. Either there's some assignment to its variables that makes it output 1, or there's no such assignment. And we want to produce an instance of 3-set, so we need to produce a 3CNF formula which has the same feature that, either if this was satisfiable, then this thing should be satisfiable, meaning that there's an assignment to the variables that makes it output 1. Or if this circuit set instance was not satisfiable, then there should be no way to set the variables here so that it outputs 1. Okay, so one of the things that's tempting is to observe, well, okay, circuit set is a big instance, is a big Boolean circuit, and here I'm supposed to produce a circuit of a certain type. It's supposed to be just like a big and of ors. So maybe I can just sort of kind of come up with an equivalent circuit that computes the same function as the circuit that was the instance of circuit set. And that would be a perfectly good reduction if you could do it. So the thing to just keep in mind, you have to maybe play around with it a little bit, is that it's very easy to come up with circuits where if you try to make them have this and of or format, the smallest and of or format will be exponentially large in the size of the circuit. Okay, so you can't carry out the reduction by just taking the circuit that you have and trying to massage it into the format of a 3CNF formula. Okay, maybe some of you already could see that, but that's not going to work because in general that will take, that'll blow things up by an exponential. Okay, so we have to do something that's a little more clever. And remember, a reduction just gives us a lot of freedom. So we just have to produce some instance of 3-set, a collection of clauses that are simultaneously satisfiable if and only if the circuit is satisfiable. And to do that, we're going to do the following trick. So let's sort of set the stage. So we're given a circuit, instance of circuit set. It has variables x1 through xn. And it has a bunch of gates. They are AND gates, OR gates, or NOT gates. And let's give names to those gates. Let's call them G1 through Gm. Okay. So our reduction, which I'll call f of c, is going to produce a bunch of clauses that together are going to form the formula phi. And those are going to be clauses which involve variables x1 through xn, just like the circuit had, and G1 through Gn. So we're going to treat each of the gates as having an associated variable, G1 through Gn. Okay, and now remember, a clause is one of these, in the earlier slide, it's a parenthesized expression with the or of 3 literals. variables or the negation. And a perspective that's useful here is that a 3-set instance, so a 3CNF formula, is satisfiable if and only if all the clauses are simultaneously satisfiable, meaning there's some truth assignment to the variables that makes every one of the clauses simultaneously true. And because they're connected by an and, that's exactly what you need to make the whole formula true. Okay, so the way we're going to proceed is we're going to produce a bunch of clauses that enforce that these gate variables G, I'll call them gate variables, take on the values that they should take on, that they would take on if the circuit was functioning the way a circuit functions. And I'll say what I mean by that in just a minute. Okay, we're going to throw together a bunch of different clauses, one for each gate, so that all together, if you satisfy all those clauses simultaneously, you basically must be setting these gate variables in the way that they are set as the circuit functions, and that will give us the sort of hook that we need to carry out the reduction. Okay, so here, so I guess I sort of said how the reduction works. For each gate, I'm going to produce a couple or 3 clauses that I have to sort of throw into the bag, and then the collection of all those clauses at the end is going to be our instance of 3-set. So let's start with a negation gate. So let me tell you what I mean by this picture. So the gate is G sub I, it's a negation, so it has one input. And now that input might come from another gate, or it might be one of the variables x1 through xn. I'm just calling it z in this slide. It could be either of the 2 things. And whatever it is, we produce from this gate the following pair of clauses. And so gi or z, and not z or not gi. And the thing to notice about this pair of clauses is that that is logically equivalent to this Boolean expression here, that z is true if and only if the negation of gi is true. Okay, in other words, z and the negation of gi have the same value, or z and gi have opposite truth values, which is exactly what should happen when you have a negation gate, right? The gi gate value is the negation of z. And actually, if you don't want to sort of carry out the manipulation yourself, you can just look at these 2 clauses and see that the only way to satisfy both of these clauses is if gi and zi have opposite values, right? Because if both of them were true, for example, then this clause would not be true. And if both of them were false, then this clause would not be true. But if you have one true and one false, then you can satisfy both clauses simultaneously. Okay? So this pair of clauses enforces the assertion that gi has the opposite truth value as of z. Okay, so what should we, so that's for negation gate. Now let's take care of the other 2 kinds of gates. So we have I guess an OR gate next on this slide. So an OR gate, it's one of the gates in the circuit. It has a gate variable g sub I associated with it. It has 2 inputs. Let's call them z1 and z2. Again, the inputs might come from other gate variables. It might be other gate variables, or they might be other inputs, x's. For this OR gate, we will produce these 3 clauses that are listed here. And those 3 clauses enforce the following, they're logically equivalent to this thing in red, which asserts that gi has the same truth value as z1 or z2, which is exactly what gi is supposed to do. Gi is an OR gate. Okay, and so you have to sort of carry out a little manipulation, multiply things out, and then simplify them so that you get it and get it as a collection of ORs. But indeed, this works. And you can also just look at these 3 clauses and check for yourself that I don't know, if z1 and z2 are, let's say, both false, then gi is supposed to be false, right? And so if the z1 and z2 are both false, and you somehow set gi to be true, then you would not satisfy these clauses, right? In fact, you would not satisfy this last clause. Okay, so you can go through and try it out carefully, and you'll see that exactly the ways in which these clauses are satisfied are the ones in which gi takes on the value of z1 or z2. Okay. So we've taken care of the nots, the ands, the ors now, and then we have to do the ands, and not much changed here, but so between the two slides. So now we're doing and. So we have to look carefully. There's the GI is now an AND gate. It has two inputs just like before, Z1 and Z2. And then here are the three clauses that we're going to sort of throw into the collection of clauses that we're building up. And they are logically equivalent to this assertion that Z1 and Z2 is equivalent to GI, which is just what we want. Okay, so you go through, in your reduction, you go through each gate in the circuit and you throw in the collection of 2 or 3 clauses that are, we've just specified, and throw them all together. Okay, and those clauses collectively all constrain these G variables to take on the values that they actually take on if you plug in a certain input, Boolean input to the circuit. And then the last little thing we need to do for our reduction is that we need to assert in our reduction that the 3-set instance, the circuit outputs 1. And so our reduction will add one clause, it's just a singleton clause, G sub m, where G sub m is the output gate. And that's a clause that can be satisfied if and only if the output gate outputs 1. That's the intention. Okay, and that's our full reduction from circuit set to 3-set. So you go through gate by gate, throw in the 2 or 3 clauses to your collection, and then this one final clause for the output gate. Okay, so let's check to see if this in fact did what it was supposed to do. So is this computable in polynomial time? This time I think it's pretty easy, right? It's a simple transformation. You just have a collection of 2 or 3 things that you need to add to your collection and just write them out one by one as you go through the different gates of the circuit, so it runs in time proportional to the number of gates of the circuit, which is the size of the input. Does yes map to yes? So if I have a yes instance of circuit set, did I produce a yes instance of 3-set? Let's check. So if it was a yes instance of circuit set, that means that there is some setting to the x variables that causes the circuit to output 1, which is satisfying assignment. And then I claim, well, if you just go through and assign those x values to the x variables, the ones for a satisfying assignment of the formula that we've built up, and the gate values of C when evaluating x to the G variables of the formula that we built up, then that gives a satisfying assignment, right? Because every gate variable in our formula phi you will assign it the value that the circuit assigns it as it evaluates the value x, and all of those clauses will then be satisfied, including the final clause, because the output of the circuit on this input is 1. So that all told, that's a satisfying assignment because you simultaneously satisfy all the clauses. So that's yes maps to yes, and then no maps to no. We have to argue that if the circuit was not satisfiable, then the formula that we built up, the 3-set formula, is not satisfiable. And we'll do that by proving the contrapositive, as we often do in NP completeness reductions. We'll show that if the formula that we built up is satisfiable, then that had to imply that the circuit we started with was satisfiable. So let's do it step by step. So if we have a satisfying assignment to our formula phi, it assigns values to the x variables, to the g variables. And what do we know about that? We know, well, let's work our way down. We know that the output gate variable g sub m must be assigned 1 because we had that singleton clause at the very end, right? And every other gate has to be assigned the value it would take given the values of its inputs, because that's what our clauses forced, right? That was the only way you could satisfy those collections of clauses, 1 for each gate. And you have to satisfy assignment if we're talking about phi being satisfiable, so there's some assignment that satisfies all of these clauses simultaneously. Well, then if you work your way all the way down to the x variables at the input level of the circuit, the assignment to the x variables must therefore be a satisfying assignment for C, because they must be consistent with the x variables and the g variables all must be consistent with the evaluation of the circuit C gate by gate. And it must have been that circuit evaluation in its final output gate assigned to 1. Therefore, that assignment to the x variables had to have been a satisfying assignment to the circuit C. And so that shows the other direction of the reduction, the other half of the argument that if the circuit was unsatisfiable, then phi had to be unsatisfiable, and we proved that by proving the equivalent contrapositive, that if phi was satisfiable, then that implies the circuit is satisfiable. And that's the whole reduction. So that was in 2 steps, the Cook-Levin reduction that shows that 3-set is NP complete. We did it by first getting a generic reduction from an arbitrary language in NP to the circuit set language. We did that by building a circuit that mimicked the functioning of the Turing machine that decides that verifies that NP language, A, given a witness and a input. And then once we had a circuit set in our hand, instance of circuit set in our hands, we could reduce to 3-set, and we did that as we just described, going through the circuit gate by gate and adding a collection of 2 or 3 clauses, which all together, if they were all satisfiable simultaneously, had to force the assignment to the X variables, as we just noted here, to be a satisfying assignment to the circuit. Therefore, the circuit had to be satisfiable. Okay, that's all. Thanks everyone for listening.